There we go. Oh, and I need to turn on the transcript, of course. Do you still like having that? Is that useful? Yes, okay. For those of you who like it, great. If you think it's annoying, you can hide it, by the way. I think it's super annoying. So I turn it on, but then I immediately hide it. And you can also drag the box around, I've noticed. So you can move it to a different part of the screen if it's in a place that's bothering you. Hide subtitle. There we go. Much better. All right. Stop it. Hide meeting controls. There we go. Alrighty. So I realized after the fact in reading all of your answers today that question 1 was probably not worded very well because I got a lot of different answers to questions I didn't ask. But I was happy to report that most of what you said was accurate, even if it wasn't what I asked. So all good, right? So where I was going with this was the idea of what is the resulting pattern in the V matrix? How does the pattern differ when you only have a random intercept versus a random slope? So what do you think about that question? Does anyone want to tell us what you wrote down as an answer to that? No, the answer is no, I don't want to tell you. That's fine. That's a valid answer. I mean, I did phrase it as a yes-no question. If no one wants to tell, then I can talk about it. So the idea of a pattern in the V matrix. So V, as you might remember, is what you get when you put R and G back together again. So the model overall, how it describes the variance in each occasion and the covariances between occasions, that has a pattern to it when you fit random effects. So let's start with just an intercept. If only thing that's random is an intercept, so you have a random intercept variance at level ... This is a finger question. If I have a random intercept variance at level 1 or 2, and I have a residual variance at level 1, when I put those back together again, what is the pattern called that they create? 2-word phrase. First word starts with a C. CS, yes. Compound symmetry is what it's called. And more specifically, what compound symmetry says is that the variance stays the same over time and the covariance stays the same over time. The model implies parallel trajectories. Everybody changes the same. When you add in a random linear time slope, what happens to the pattern? It's no longer compound symmetry. What is it? Or what does it depend on? Any ideas? Nobody wants to be brave? How about I show you the pattern? I'll just show you what I was going for here. I have it pulled up. This is slide 21 of lecture 6. Here's your pattern. The variance at each occasion when you add random linear time looks like that. So it changes as a function of the specific time values each person has. So it's a custom V matrix for each person. That's how it handles unbalanced occasions, because the way that the variance changes is as a smooth function. So it predicts that the variance has a U shape. It's going to be a minimum at some point, and it increases on either side of that in a quadratic fashion. And it's quadratic because of this piece right here. The variance of the U1 random slopes multiplied by time squared. So that creates a U-shaped pattern of change in variance over time. And the covariance between any pair of occasions starts off with what it was for the random intercept only model, but it also has this stuff here, which is a function of the random slope. So big picture, the pattern that the V matrix has after adding a random linear time slope is non-constant. Non-constant, and it depends on the exact time values observed. I don't expect you to memorize these formulas, but having a general sense that a linear model results in a quadratic pattern of changing variance. That's what I'm looking for here. And if you have random quadratic time, the variance at each occasion is this ugly thing, which has time to the fourth, stop it, as part of it, which is where I had to make up the word cortically. It's a cortically changing pattern of variance. And the covariance between any two occasions is this messy thing, but also time dependent, just in a different pattern. So that's what I was going for. Several of you volunteered other characteristics, such that once you have a random linear time slope, the random intercept becomes conditional on time zero. That is true. If you only have a random linear time slope, then it is unconditional. Once you add a random quadratic time slope, random linear time is also conditional on time zero, and that is true. So I think that covers most of the answers that I saw. Are there any questions or parts of that you want to talk about more? Cheers. No? Goodish? Goodish? Okay. Yeah, we need the thumb sideways emoji for this. And then setting up you to be able to get through your homework with quadratic models. How the model tells you what the predicted mean is at each occasion, and how the model tells you what the predicted linear slope is at each occasion. So I gave you an example model and asked you to figure this out. Here is the answer key, that box right there. So the trick to this is remembering when to take time and square it versus multiply it by 2. That's the trick to this. When you are creating a predicted intercept at each occasion, so to me the term intercept is synonymous with conditional mean or expected outcome. When you are creating a predicted outcome at each occasion, then all of the fixed effects of the model are involved. So I need 1 of the intercept. I need however many linear slopes are as a function of time. So in this example, I had given you time 4, so I would put a 4 here. And I need 4 squared. So when you're creating an intercept, you square time as the contribution to the quadratic. So putting that all together, it would be 10 plus 3 times 4 plus 0.5 times 4 squared, which I think worked out to be 30 or something. Several of you worked out the math. In terms of the estimate statement, the programming statement, the intercept gets a 1, time gets a 4, and time squared gets a 16. So most of you got that right or were very close to it. So questions on that much so far? And several of you centered time and told me what it would be for time 3. That's fine, because I just want you to understand the function. Because once you understand the function, you can get the predicted intercept at any occasion, not just the one that's time 0. And then the other one, how does the model give you the instantaneous linear slope at each occasion? Times 2. So to get what the model says the predicted slope at any occasion is, it starts off with what the linear slope is, so I need 1 of those, and then I need 2 times the value of time that I want the linear slope for. So this mini equation right here also highlights why the linear slope gamma 1, is specific to time 0, because that's the only point at which the second piece of this would cancel out and drop. So gamma 1, the linear time slope, is what the linear slope is expected to be at time 0. It is going to change by twice the quadratic per unit time. So then to get the right answer for the last question here, I would need 0 intercepts, because what you're predicting is the slope. I need 1 linear slope, and then I would need 2 times the value of time. So it would be 1 and 8 as the coefficients that go in here. So you will get a chance to practice this, I think, in your homework. I'm pretty sure I asked that question. So any questions on those two? Okay, any homework questions? I have homework 3 up if anyone wants to ask about that. So note we're adding progressive layers of difficulty with the homeworks. Question on how do I approach question 42? Well, let's find out what 42 is. That's a computational one. Scrolling down, that's in section 4. So confidence intervals. These are not given to you directly. These are things you have to compute. So the middle of the confidence interval is, I think I have, let me pull it up. This one. Let me find a confidence interval. It's in the same handout, 6A. Rather than me telling it, I'll put it up. That. This is page, what page am I on? Can't tell. 14, it looks like. So the center of the interval is the fixed effect. So if I'm building a confidence interval for the intercept, the middle is going to be the fixed intercept. The boundaries of the interval are going to be informed by the random intercept variance, its square root. So when you get the multiplier of 1.96, which corresponds to the z-value at 95%, then it's like you're giving it roughly 2 standard deviations around the fixed effect. So you're trying to predict what 95% of the individual values would be for whatever the term is that you're predicting. So for the intercept, it would be the expected outcome at time 0. What's the 95% range around that in terms of your sample? For the linear time slope, it would be the linear slope coefficient is the middle, and the boundaries would have random linear time as part of that. And for quadratic, fixed quadratic would be the middle, boundaries would be random quadratic. Okay, does that help? Yes, okay, good. So your previous homework, homework 2, was focusing on just making SAS give you numbers and finding them, right? That was the objective of homework 2. And also to notice what happens between ML and REML. Whenever you have a small sample size, your random effect variances when estimated using ML will be too small, which translates into standard errors for the fixed slopes that go with them that would be too small. And whenever you have a fixed effect that also has a random effect associated with it, so if you have a fixed linear time slope and a random linear time slope, the standard error for the fixed time slope is going to be higher because it also contains that random slope variance as part of it. So that was what the previous homework was focusing on, is just those ideas. Now I'm looking to see that you can map the answers that SAS gives you onto ideas, right? So if I'm asking, for instance, what is the estimate quantifying within-person variation and well-being? That requires you to identify, okay, what is the model parameter that goes with that idea? Now, where is it on my output? So levels of complexity here, and then filling in the drop downs. So note that each of these has a question number in front of it. So if you have a question, you want to email me, you can say, I have a question about question 55, and I'll know what you're talking about. And after you turn in your homework, you will get to see these answers turn red and green as well. So you'll get to see what would have been correct. All right. Any other homework questions while we're on this? Not yet? Then I have some good news for you. Do you know what I did over the weekend? I got my second COVID vaccine. So there's that. That was Sunday. But what I got done before Sunday was homework 4. So that is available to you. Yeah, the second shot was not fun. The first one wasn't very much fun either, but just take it, just plan it when you need it, like the next day off would be my recommendation. Arm hurts, brain is fuzzy, feverish, all that fun stuff, but beats having COVID. But yes, homework 4 is available. Homework 4 is a bit of a beast. It is a piecewise model that also has quadratics. I mean it's in a good way. It's challenging work, as my son would say. It's well within the scope of what's possible. It's just extending what you're doing with another level of complexity. The story for this is based on a true story. It is a piecewise model about changes in stress leading up to people taking the bar exam, and then changes in stress after taking the exam and then while waiting for their scores. So this came from a student when I was at the University of Nebraska. They had a combination PhD JD program where you could go through law school and get a PhD at the same time. Yeah, I know. And so those people were there a long time, let's put it that way. But they got law school paid for, which was the allure of doing it. So like saving several $100,000. And in this class, one of the students was currently studying for the bar exam and talking about how stressful that was. And I thought, well, that would make a good homework. So there you go. The same student, by the way, who taught me that I am the hoe in M+ output. Same person. So thank you, Lindsay, for that. Yes, bar exam, very stressful. So the story is that, stress doesn't go away when the bar exam is over because you got to wait for your scores. And since it's such a life-changing kind of result, then there's a lot writing on it. So homework 4 is not due until the 26th, so like 3 weeks or something. So plenty of time to work on it. And I just wanted to let you know that it is available if you have extra time and want to have something to do. I also put up your next formative assessment. So that's due in 2 weeks as well. So you can continue working at your current pace or work ahead as suited. All right. So then, put this away. If there's not any other questions about that stuff, are you ready to talk about piecewise models? Yay! So these are also known as linear splines. So if you've had my 6242, we did piecewise models in there, but you may have seen linear splines in regression, maybe? Does that term sound familiar? No? No? Okay, well, great. It's brand new stuff then. Excellent. I love it when that happens. I think piecewise models are super duper useful. So and they're not that hard to do. So I wanted you to have some exposure to this. So let's pick up on, this is slide 26 of lecture 6. So piecewise models in general carve up a quantitative predictor into sections, and then you can look at what the effect of a 1-unit change is within each distinct section. So in the context of longitudinal data, piecewise models map directly onto multiple intervention types of studies where you have a slope for occasions that happen before and a slope for occasions that happen after. So for instance, one of my students happened to have data in an area where a tornado had hit, and they were collecting data before the tornado hit, and then the tornado hit, and they decided to collect more data afterwards. So that's a very realistic setting for when a piecewise model would be appropriate. Something happened in the middle, and you're not the same afterwards. And so it may be of interest to know how change changes before and after some event. So here is a former student's example. Back when I used to do projects, and I had only 12 people in a class so that I could actually make that feasible. She had a multiple intervention baseline design here. They were trying to improve some outcome in 5th graders. So they measured the 5th graders in a classroom for several occasions in which nothing was supposed to be happening to get a baseline. They then introduced some kind of intervention, and the kids got better and better and better as time went on. And then they took the intervention away, and they started sucking again. Drops back down immediately, flat slope, brought it back, hooray, back up with the positive slope. So if you just look at this sort of up and down trajectory, visually this provides fairly strong evidence that whatever they were doing is causing the change, and it's not just due to natural sorts of maturation processes. That you can also have control groups where you have nothing happening and do that as a comparison. But this is a perfect example of when you would want to fit a piecewise model. If you viewed this as a continuous trajectory, that part would be quadratic and that would be a cubic, and then we'd have to change directions again to a quartic. It'd be like a 7th order polynomial through this thing, like someone trying to do the worm through your data. I'll spare you that image. I'll just do the arm instead. Like, no, but that doesn't actually correspond to the design of the study. They wanted to know if there was a acute improvement in performance after they introduced the intervention, and they wanted to know if they continued to improve, and they wanted to know what happens after they took it away. Would they maintain or would they fall back down? And so these models can be expressed as distinct slopes through each of these phases, as well as shifts in intercept between them, so that you can test what I would call jumps and slopes within that. So do any of you immediately think of an example in your world that this might be useful for? Because I can give you some others as well.
I've got one.
Yes.
So we're looking at children who are about to come to an autism evaluation, but they don't know what the diagnosis is yet. So pre-evaluation and post-evaluation.
And what do you expect to happen post-evaluation that wouldn't have happened otherwise?
Changes in parental behavior when they now know that their child has a certain diagnosis.
Makes a lot of sense. Maybe not the child, depending on how old they are, if they understand what's going on, but certainly those interacting with the child makes sense. Yeah, that's a great example. And in this case, you know when the doctor's appointment was in which this information was conveyed, right? That doesn't have to be the same occasion for each person, but you do have to know when that was. So that is the critical thing here. To fit these models yourself, you must know where the breakpoint is. So in such a design, you would align the data such that time zero is the easiest thing to do would be when the diagnosis was given, and then you would have one slope operating through the negative part of time and one slope operating through the positive part of time. Other examples, so back from when someone of the psychology students was studying stress responses in infants, and she described a study where they had a baseline period where the baby was sitting on mom's lap and playing and all happy, and then they made the baby mad. Like they pinned the baby's arms down or took their toy away or whatever and watched the baby freak out and measured their increase in cortisol and amylase. And then they calmed the baby down, gave it back to mom, gave the toy back, whatever it was, and they watched the decline in cortisol. And that was the idea of reactivity from baseline up to freak out baby. And then from freak out baby back to normal was recovery. And that's great, except that she only had 3 occasions. With 3 occasions, you can only have 1 random slope, not 2. So either babies could differ in recovery or they could differ in reactivity, but not both at the same time according to that model. So for 3 occasions, a piecewise model where you have 1 slope and 2 slope is the same thing as a saturated means model. So the real benefit of this approach is when you have multiple occasions within each phase with which to distinctly identify each type of slope. Another one I can think of from one of the marketing or management students was looking at blue laws in states. It used to be a rule in states that you couldn't go shopping on Sundays, like all the stores were closed. I know that sounds crazy to me. Like all of my youth, like when I was a junior high and high school, like I spent every Sunday at the mall, like it was my job. So I can't imagine a situation in which there was no stores open on Sundays, but that used to be a thing. And so then they had economic data looking at various trends in what happened before the blue law was repealed versus after. So in all of these instances, though, they know where the breakpoint is because it's something that happened and it's measured, and it can be per person, but you know when it is. In contrast, I once had a developmental psych student ask me, okay, so can I use this for like before puberty and after puberty? What do you think? Those of you who have children or have studied developmental psych, does puberty just happen one day? Like all of a sudden you're past it and you're good? It's like, and that was my question back to him. It's like, sure, you can do that. Tell me what day puberty happened. So for something like that, when it's a fuzzy boundary and you're not really sure, these types of models would have to be modified to become what's known as latent versions of these, where one of the parameters being estimated by the model is where the break is. So the versions that I'm going to teach you are such that you would code the variables in recognition of a known break point for each person. Alternative versions of this model can actually estimate where that break is, and you can make the break be random, such that it varies across people. You need a lot of data per person to estimate those sorts of models. I do have some example code using NLMix that I can share if you're interested in doing anything like that. You can also do it in some programs, SEM type programs as well. So we're operating under the assumption that we know where the break is in what we're covering today. So here's another example, cortisol. Remember I told you I was a real life psychologist. I have a PhD in everything. I know about cortisol that it increases from when you wake up in the morning to 30 minutes later, which is a term that the people that I stole these data from called the morning rise, and then decreases throughout the day and into an afternoon decline. And so if you have measured variables for when each of these 4 occasions would be, so wake up 30 minutes later, lunch and bedtime were the instructions given to when they were supposed to stick a wad of cotton in their mouth, chew it, and mail it off to someplace. Fun studies. Then you can fit a model that looks like this. So if I put the first occasion as the intercept, then I can put the common 0 points for both of these pieces here. If occasion is 2, then I want to know how long it's been. So it's supposed to be 30 minutes, but people aren't doing it exactly on time. The second slope isn't active yet. The second slope then kicks in at the second occasion and measures how much time has passed relative to the second occasion at each subsequent occasion, whereas the first slope shuts off at the first occasion. So then putting it together, the purple line, that first variable, measures the change from time 1 to time 2, and the orange variable measures the change from time 2 to 3 to 4. But if you look at this line here, does it look like this straight line would be a good fit for these data? Not really. It needs something bendy. So given that there are 3 occasions in this second piece right here, you could add a quadratic time slope, and then it would perfectly saturate the 4 means, because then you'd have an intercept, morning slope, afternoon linear slope, and afternoon quadratic slope. So that would be the 4. All right, so what it would look like then to fit a model with 2 slopes would look a lot like the previous quadratic model, just with a change in the variables. So if I had a model like this where I was interested in looking at individual differences in the intercept, in the morning change, and in the afternoon change, it would look a little something like this, where I have an individual intercept, a morning slope, and an afternoon slope. Because I've got my 3 betas at level 1, I got my 3 level 2 equations, 1 for each. So then the red part is the fixed effect, the blue part is the random effect, and so I would have a fixed intercept and a fixed slope for each piece, and potentially a random slope for each piece as well. So exact same set of concepts, just redefining what we mean by time. So all of these models live or die by the accuracy of coding these variables. This is the tricky part, is to make sure that the slope variable that you create accurately captures the range of time that you want it to. And so this way of parameterizing it that I showed you with this, making it this way, directly gives you the change during each of these periods. But there's another way to do it that I'll talk about in just a second. So each of the random slopes, same definition as usual. It's how far off your slope is from the average slope given by the fixed effect. And given that I have 2 random slopes related to time in this model, I need at least 4 occasions to fit this. That's why if I only had 3 occasions, I couldn't do this model. You can't have random slopes for both. There's not enough information. Because then you would perfectly capture all of the variance and covariance using the G matrix without a residual. Okay, how are we doing so far? Yes? Okay? All right, excellent. So our data. These are the response time data that we've been playing with. And do you remember the conclusion that we came to at the end of last week? We had fit quadratic models, and how well did they recreate our observed means? Do you remember what happened? Didn't work. Yeah. So we did a test of absolute fit, adding in session-specific contrast to saturate out the means, and those contrasts improved model fit, which means that the quadratic model didn't fit. So here's another idea. What if I piecewise this thing? Now, I will be the first to admit this is not a theoretically driven model. This is a data-driven model. I stared at it and went, it kind of looks like it could be two slopes. So I have my orange slope, which I'm going to call an early practice effect, the initial effect of having done this task once, and then a later practice effect. So a lesser degree of improvement after session 2 until session 6. And based on my PowerPoint drawing ability, this looks pretty good, don't you think? Looks like this could work. So how do I set up the variables then to give me these interpretations? In chapter 6, I talk about 2 different ways of setting up the model, and I will show you both of those ways using these example data. So the first way is coding the time predictors so that each directly captures the change during its period. So in this case, I have my orange predictor that is early practice. I'm going to call that slope 1, 2 because it's the slope that measures change from session 1 to session 2. Creative name. And the way that I coded it is to make the first occasion the intercept, so keeping it at the same place as we had before, and going from 0 to 1, because session 2 is 1 unit in time past session 1, but then I want the first slope to shut off. So I shut it off at the last value for time. So functionally, if all I had in the model was this orange predictor, the pattern of change it would predict is this. I'd say response time declines from session 1 to 2, and then it doesn't decline anymore. So it's kind of like a dummy coding thing, where I'm setting off session 1 from all the others. So orange captures the rate of change from session 1 to 2. Then purple shows up to fill in the gap. So purple picks up where orange left off and measures the subsequent changes after session 2 to 3 to 4 to 5 to 6. So then purple is the rate of change from session 2 to session 6, what I'm calling later practice, or slope 2-6 as I will call it in SAS. So if I only had purple by itself in the model, the pattern of change that it would predict based on this coding scheme would be to lump session 1 and 2 together and then differentiate sessions 2 to 6 like this. So when you put it together, the change starts off following the orange trajectory, but then it hops on to the purple trajectory. Kind of like trains. This is sounding like a subway. Like I follow the orange line up until stop 2, and then I hop on the purple line, and that gets me to my stop. So each of these slopes directly captures the rate of change during its period. And I know where the intercept is because I set it up to be the occasion at which both of these slopes are coded 0. You can put the 0 point wherever you want. I just kept it at the beginning because that's how we had it for all the other models to be examined. All right, so that's one way of doing this. The other way of doing this is to, instead of representing both slopes directly, is to let one of them represent a difference in slope. So the alternative coding scheme would look like this. So I'm going to have a predictor that I'll call slope 1-6 and a predictor called slope 2-6. And slope 1-6 looks very familiar. If you look at the numbers here, we called this time last week, right? It's just session minus 1. So if I only had the first slope in the model, that's the same thing as just a linear time slope. What purple does, though, is make an adjustment to the slope. Purple steps up here and gives me a difference in slope. How much the slope has changed after session 2 is what purple is telling me here. So when might you do it this way? For any situation in which change is expected regardless of what you do, and you are trying to measure an additional impact on change. So like if I go into my son's kindergarten class, do you know what kindergartners do if you don't have any sort of intervention? They learn. They get better at things. They get better at learning their letters and adding numbers together and tying their shoes and zipping their jacket. They learn things, right? That's called school. If I wanted to measure the impact of some sort of additional intervention, some extra module that I want to introduce, and I want to know if kids learn more under my extra condition, then I don't want to know how much they're changing during the intervention. I want to know how much more they are changing during the intervention relative to what they would have done anyway. So for those sorts of situations in which change is expected as a default across all periods of time, you can specify the model to instead give you the increment to change after a certain point. So this is a little bit harder to wrap your head around sometimes, but it can be very useful for those sorts of designs. The good news is that there is a one-to-one correspondence between these two models because each will give you three of the three pieces of information, and the third is a linear combination. So if I fit the previous model that tells me change from slope 1 to 2, and then change from 2 to 6, I can ask for the difference in these two slopes as an estimate statement. If I do it this way, and I get change from session 1 to 2, and then differential change from 2 to 6, I can ask for what actual change in 2 to 6 would have been as an estimate statement. So if you know 2, you can always get the third. So I will show you how this works. All right, you want to see it? Why not? So then what do the fixed effects and random effects tell you? Same thing as usual. The job of the fixed effects, the fixed slopes, is to talk about average change over time. What does the average trajectory look like? The job of the random effects is to capture individual specific deviations from that trajectory, and the model estimates the variance across people in those random effects. So if I have a random intercept, that's individual differences in the intercept at time 0. If I have a random slope 1, 2, individual differences in the change from 1 to 2. Random slope 2, 6, individual differences in the change from 2 to 6. The other way of setting up the model, the deviation slope way, the corresponding change in how slope 2, 6 is interpreted as the difference in change then propagates to the random slope. It would be individual differences in the difference in change, individual differences in how change has changed after the hinge point. So you just have to figure out which of these is going to be more useful to you and then go down that route accordingly. Okay, so let's see it, shall we? I've got example 6b queued up here, and we can go through these models and see how they fit our data. All right, are you with me so far? It's not so bad, right? It's a coding scheme. You are finding ways to trick the program into giving you the information that you want. So here is the syntax to do this in each of our programs. And I have written this out for the sake of transparency. There are faster ways to code this that you can certainly use, but I wrote it out so that it would be clear. So in this example right here, I'm making 3 total new variables. I have slope 1, 2, slope 2, 6, and I also have time 1, which is from before. So I have conditional logic here to create slope 1, 2 and slope 2, 6. Based on if it's this session, these are the values that I want to put in, and those are the same values that I took directly from, where is it? Where's my table? This table. That's where those came from. And then I am going to do an absolute fit test, so I have the dummy codes from before as well. So then instead, it's a longer set of code because each line is a separate statement, but it's the same way. If session is 1, then I want it to be 0. If session is greater than 1, I want it to be 1. For the second slope, then it's 0, 0, 1, 2, 3, 4. And I have an example online as to what this would look like if you had unbalanced time. This is a coding scheme that assumes everybody has the same possible sessions, and therefore you can stick in integers for the time values. And folks, in R, I have a which. Thank you, Jonathan, for helping me find this. Conditional logic in R, not if, but which. I'm sure there's an if somewhere else, but this is how it worked. And then the dummy codes as well. All right. Okay, I don't have all the dummies in R for whatever reason. I have them in the other packages too. I don't actually need these ones, but I have them here anyway. Okay, so looking at the code to create the slopes, are there any questions about how that's working or why the values are what they are for this example? The idea of building a table like this for your homework 4, by the way, highly recommend. Build a table like this to sort of visualize what the code needs to do. And actually in section 2 of homework 4, the first like 5 or 6 questions are asking you about values in this table to make sure that you've created your predictors correctly. So this step is important to conceptualizing how the code is supposed to then create new variables to represent distinct phases of time. All right. So we're good? Gonna see it? Good enough? Okay. So then my first model here, continuing off from the list before, so that's why it's 4A, because we had 1s, 2s, and 3s in the previous handout. I am going straight to a model that has both fixed slopes, but no random slopes. So previously I had linear time only, and then I added random linear time, and then I had quadratic time, and I added random quadratic time. I'm doing it differently here on purpose. Can you guess why I'm going straight to a model in which both of these slopes are included simultaneously, rather than putting them in one at a time? So why am I putting them in both at the same time as opposed to doing it one at a time? Because you would never have just one. Yeah, kind of like candy, like Reese's Pieces or something. You never have just one. But yeah, if I had just one, they don't mean the same thing. Another suggestion, it's the most complex model, so you can drop one if you don't need it. This is true. Although I would not want to drop it until after I've verified that it isn't needed either as a fixed effect or a random effect. So I got to hang in there until I know that much. But yeah, they work together. So the interpretation of slope 1, 2 as representing the change from 1 to 2 specifically would not hold if this purple predictor were not in the model. Otherwise, it would be 1 versus all the others. So it's the same logic when you first learned how to do dummy-coded predictors for categorical variables. You have to put all of the dummy codes in the model at the same time for them to mean what you intend them to, otherwise it doesn't work. Same thing here. So the slopes work together to capture the overall trajectory. They're not hierarchical. They should go in simultaneous. That way each of them can do their respective jobs in terms of which section of the trajectory they are each supposed to represent. So I have 2 fixed effects, 1 random intercept. So based on the fact that I only have a random intercept, what kind of change am I predicting in this model? With only a random intercept, what kind of change am I predicting? This is a gesture question if you want. I am predicting piecewise linear, but do people get their own? No, parallel change. This model has two fixed slopes in it that do not have random slopes attached to them. Parallel change. So people are allowed to start out at different places because they have a random intercept, but the differences between people are expected to hold in parallel all across the trajectory. That's a very strict assumption. That's a compound symmetry model. But it's a jumping off point. That way we can test whether or not the random slopes are necessary. So once I make my new slope 1, 2 and slope 2, 6 variables, I put them in the model as usual. So they go in here on the model statement. Note that they do not go on the class statement, meaning I am treating these as continuous predictors. They do not go on class. They only go on model. And here they are in the Stata code as well. And here they are in the R code in Elmer today. Now the rest of these. These estimate statements are generating what the model says the predicted outcome should be at each occasion. And note the values that go in the estimate statements are the exact same values that went into creating the predictors. There's a one-to-one correspondence there for a reason. The values that go into these estimate statements to create predicted outcomes are the values that correspond to the predictor for that occasion. So that's why for slope 1, 2, it's 0 for session 1, it's 1 for all the others. For slope 2, 6, it's 0, 0, 1, 2, 3, 4, because that's how the predictor was formed. So two different variables to represent time in this model. And then last but not least, I'm asking for the difference. Is there a different rate of change before session 2 versus after session 2? That's my estimate statement to give me the difference. So the same stuff. Stata code looks very much the same with the addition of the asterisks to make the multiplication by the constants explicit and the plus signs to make the addition explicit. R, of course, a little harder, but you get your values of your coefficients inside each of these little functions here that corresponds to the same constants that go into the estimate and lincom statements. And then the linear contrast right there at the very end for the difference in the slopes. Give one of them a -1 and the other a 1. All right, any code questions so far? Any that you need to hear again? Are we good? Well, good news. If you want to hear it again, I have a YouTube channel. You can hear it as many times as you want. What's very funny though is that inside my YouTube account, I have like all of my subscriptions to other people's YouTube channels, like the Colbert Report and Twins, the New Trend. I don't know if you've spent any time on that website, but that is such a guilty pleasure of mine. It's two, I think they're like, they look to me to be 14, but I think they're actually 22 or something. These two people who watch music videos that they claim to have never seen before and give reactions. And it's just funny. Today I watched them react to Belle Biv DeVoe's Poison. And I believed that they had not seen it before because they pronounced it B-I-V. Belle B-I-V DeVoe. I was like, okay, that's a legit, like no one's heard this before. But they enjoyed it. They very much enjoyed it. It is a great song. Never trust a big butt and a smile, right? I mean, they said it best. But anyway, the YouTube puts my class videos as like suggested as to what I want to watch next. I'm like, incorrect. I do not want to watch my class videos. But I do have to click on them to make sure that they loaded properly and that they have audio and stuff. So it thinks that I want a subscription to my own channel, but it is incorrect. But you can watch it as many times as you want. Or you can watch them. I'd actually recommend them. They're much more enjoyable. But anywho, here's my model. So our matrix, what's in here? We'll do a little vocabulary review. What's that number tell me? The number on the diagonal of the R matrix is 34,098. What is that? Oh, you know this one. I know you know this. What is that number on the diagonal of the R matrix? I'm watching the chat window if you're all feeling shy. Are your fingers shy too? It's a variance. Which one? Residual variance. There we go. At level ... 1. Yeah, that's my level 1 residual. So that's all the individual deviations from the average trajectory that's predicted to be the same for everybody. So after you factor in that average trajectory and your random intercept, this is how far off each occasion is from that prediction. So taking the parallel lines, bumping it up or down based on the random intercept, and then the e's fill in what's left. My G matrix. That's my level 2 random intercept variance. So in this model, it's person mean differences because it's a parallel change model. So the person mean is the same, is sufficient because it would be the same at any occasion. Here's my V put back together again. The diagonal of V is the total variance at each occasion. That the model says is the same. This is a compound symmetry model so far. Correlation across occasions is the same. I would call this an intraclass correlation, but it's a conditional intraclass correlation after controlling for which occasion is which. This is the one instance in which this likelihood ratio test that shows up by default, it shows up in Stata as well, is useful. This is telling me whether or not that random intercept variance is significant. Cough, cough, homework question. So this is the effect size that this significance test is referring to. This likelihood ratio test is testing whether or not the proportion of variance that's between persons in the random intercept at level 2 is different than 0. Then we go down to our estimates. So first question, are my two slopes significant and how do I know? Thumbs up for significant, thumbs down for non-significant. Yeah, this is a softball question. Like a wiffle ball question even. Yeah, thumbs up. For fixed effects, stare at the p-value. That's allowed. So interpreting these things though, that's the trick. This is gamma 0, 0. What is this telling me? What does the intercept represent in this model? The intercept of 1961 milliseconds is the predicted mean at time 0. Yep, not the actual mean, but the one that's predicted by this function. So, yes. And it's time 0 because that's the way I set up my pieces. So you control where time 0 is. You can put it wherever you want. I like it at the beginning. It makes the most sense to me. So at time 0, people are predicted to take 1961 milliseconds to do this task. Slope 1, 2. That tells us what? It's in the name. Yeah, I'll take that. It's a negative slope. Response time is doing what? Yeah, going down, decreasing. Yep, people are improving because shorter or smaller response times, however you want to talk about it, is a good thing. So this is the rate of change between session 1 and session 2. Given that there's only one difference, you can just think of it as just the straight difference. This is how much faster people are at session 2 relative to session 1. On average, they are 163 milliseconds faster. Then from here, what happens? Are they still improving? Are they improving the same? Doesn't look like it. Still going down, but not as much. Yeah, less downer. That's what they're doing. They went from more downer to less downer. But they're still improving, otherwise the slope wouldn't be significant. So given that this slope is covering the territory between sessions 2 and 6, it is a rate. So 32 milliseconds per session is the rate of linear decline that this phase predicts. So slope 2-6 is a linear slope. It's just operating from session 2 to 6 because of the way we coded the predictors. Do you see anything on this page that would allow me to answer the question, do I really need 2 slopes, or can I just like smush them together and call it good? Because 163 and 32, are those really different? They kind of look different, but I can't really tell from this. What do you think? Yeah, I asked the question down here. So our friend estimate statement to the rescue, a linear combination. So the difference of these two slopes is 130. More specifically, slope 2-6 is less negative. That's why the difference is positive, because of the way I coded this. And that difference being significant indicates that no, I shouldn't have 1 slope, I need 2. So these models are only going to give you 2 out of 3 things. You got to find the third as a linear combination. And here are the predicted response times at each occasion. Here are the equations for how I got them. The values in parentheses are the corresponding values for how I created the predictor variables. And here's how I did. Not bad, right? This is pretty good. So we got the mean side taken care of. In the book, I added a quadratic component to the second piece here, and it didn't help anything, so we don't need that. Effect size. So each of these slopes is significant to describe the overall change over time. We can get an effect size via pseudo R-square. So I wrote a little macro in SAS to do pseudo R-square. What it does is use the saved table of covariance parameters from each of the 2 models and then calculate it, but there's also a spreadsheet for this. So you can use the spreadsheet and type your numbers in, or you can write your own little macro in Stata or R. Knock yourself out. I haven't learned how to program in those languages yet. But this is telling us that the level 1 variance, the residual variance in the R matrix, went down relative to an empty model by 24%. So 24% of what we initially called within-person variation was due to average change over time. And the other value here for the random intercept is a negative pseudo R-square, because anytime you explain level 1 residual variance only, level 2 variance goes up. Has to. They're yoked together. Okay, questions on that much? So from here, let's see if people need their own slopes. Given that these 2 slopes are not hierarchical, I don't have a motivation necessarily to test one before the other, but I'm just going to go in order. So where's Waldo? What's new in my equation here relative to the previous model? We got 1 vote for E. E was there before, though. If by E you mean new error term, that is correct. But another vote for U1. Yeah. U1I. That's the new thing right there. So that is allowing individual differences in slope 1, 2. So asking the question, are there differences between people in initial improvement from session 1 to session 2? So slope 1, 2 goes on my random line. Slope 1, 2 goes after person ID here in Stata. And slope 1, 2, scrolling over, shows up at the end of the formula in R. So exactly the same as you already know how to do, just changing what the slopes mean. From just having them be linear to more specific, it's linear between sessions 1 and 2. So now the overall R matrix has less variance in it because it has been reallocated. So here's my G matrix. It's now 2 by 2. So I have added how many things to my model in adding that U1I term? How many parameters have I added, and don't say 1? If I add a random slope to a model that already had a random intercept, how many parameters have I added? 1 vote for 3. 1 vote for 2. The answer in this case is 2, because we added the random linear slope variance for the first slope and its covariance with the intercept. In the next model, it'll be 3. The intercept at time 0 and the rate of change in slope 1, 2 are negatively related. So people who start out higher have a more negative rate of change. That stands to reason. If they're slower to begin with, you have more room to improve. Now this V matrix here, take a second and stare at it. Note what has happened to my model implied pattern of variance and covariance over time based on this. How would you describe the variances over time? This is the first time you've seen something like this. Are the variances over time the same or different? Yeah, 2 to 6 are all the same. Yeah, compound symmetry split. That's exactly what I would call this. From session 2 to 6, it's compound symmetry. Why is that? From session 2 to 6, it looks like compound symmetry. Why is the question. Any guesses? Because we haven't added a random slope 2, 6. Yep, because it's only random for slope 1, 2. Exactly. So the part of the trajectory that only has a fixed effect is a compound symmetry part. So it's like partially compound symmetry. Most of it is, but partially not. So that's why you have this weird sort of half and half pattern. So this is the problem, by the way, when you have a piecewise model with only 3 occasions. Like the angry baby study I mentioned a little while ago, reactivity and recovery. If you can only have one of the 2 slopes be random, then what you're saying is that the variance across time for the other slope is the same, which is probably not true. So in that situation, I wouldn't do random slopes at all. If you only have 3 occasions and it's a piecewise model, I would unstructure that thing in a heartbeat. Because I don't want partial compound symmetry. Then testing whether or not it's helpful, likelihood ratio test as usual. And that says yes. Looks like people do need their own rates of change from 1 to 2. So then we pick up the random slope on the second half. Here's my friend U2. Now how many parameters have I added to the model? And adding this one U2 here, I've added one variance. And what else? 2 covariances that go with it. So slope 2,6 on the line. Because there are 3 random effects on here, it's a 3 degree of freedom change. That's how you can remember it. One second here. So we add slope 2,6 here in the stated code. It's on the end of the line here in the R code as well. So same idea as usual, adding random effects. Here are the 3 new parameters that we added. The variance from 2 to 6, and its covariance with the slope that was already there and the random intercept that was already there. And now we have a V matrix that looks a little more reasonable. It's 2 different sets of quadratically changing variances, one for each piece. And does that help? Yes, it does. So that means what? If I added random slope 2,6 and it significantly improves model fit, that means what? We keep it, yes. So if you were writing a results section, you would say -2 log likelihood difference is 44 on 3 degrees of freedom, p less than 0.01, comma, indicating, right? What's the end of the sentence? We keep it as the next sentence. The next sentence is, thus, this new random effect was retained for further models. But we need the indicating part. Conceptually, what does this indicate? Each person needs their own. Yeah, people change differently in the second half. So the fact that both random slopes added to the model means people differ in how much they change from session 1 to 2, and they differ in how much they change from 2 to 6. How about some effect sizes? Here's some confidence intervals that can describe the extent of change. So we have 3 different terms that each have a fixed and random effect. Therefore, there's 3 confidence intervals. The one for the intercept tells me that the predicted mean at session 1, which is my time 0, is somewhere between 900 milliseconds and 3,000. People are predicted to change from session 1 to 2 anywhere from a decrease of like 650 milliseconds all the way up to an increase of 322. So some people are actually not getting better at this. They get worse initially. And continued improvement anywhere from 133 in a decline to 67, meaning not improvement, but worsening. Thus, we keep it. So at this point then in our model, how many different kinds of variance do we have? How many different kinds of variance? Got 1 vote for 3. I'm going to head back up into the equation so that we can list them. Another vote for 3. How many kinds of variance? I've got 3 U's. So I have 3 different kinds of level 2 variances. Yeah, it's 4. We got friend E over here. E is why are you off your line today? I gave you your own piecewise trajectory and that's not good enough for you? No, it's not good enough for you anytime you have more than 3 occasions. There's going to be some error there. So what's happening today that makes your occasion different than the one that's predicted by your trajectory. So yeah, we can't forget about E. E is going to be explained by time varying predictors, whereas our U's here are going to be explained by time invariant predictors. That's the next unit that I'm still working on the handouts for. All right, questions? All right, then I think that's a good place to stop before I show you the other parameterization. This is the parameterization that I want you to use in homework 4, but it's going to be 3 slopes instead of 2. But I've listed some places to go for help on how that will look. But this will be the gist of it, is carving things up into sections and looking at change in each section. All right, then if there are no more questions, we can call it a day. Go out and enjoy the sunshine. Let me know if you need anything, and hope to see you Thursday. Thanks for coming. Until next time.